Smocking is a traditional embroidery technique that involves manipulating the fabric with threads to create decorative and geometric textures. Smocking comes in different types. Canadian smocking uses isolated stitches on one side of the fabric, while Italian smocking employs continuous stitches that pass through the fabric several times. A recent paper, Digital 3D Smocking Design, proposes a preview tool for Canadian smocking. Given a 2D smocking pattern on the left, it merges all the grid nodes on the same stitching line to predict a 3D smocked result on the right. However, this approach doesn't work for Italian smocking, as the continuous stitches connect a long list of nodes together. Merging all connected nodes leads to cluttered and unrealistic results. In this work, we propose a method that can handle Italian smocking. Our input is an Italian smocking pattern with front and back stitches. We first extract a coarse mass spring system in the same resolution as the input pattern and call them fabric springs. We then include the stitching lines as a list of connected stitching springs into the system. At first glance, solving the dynamics of this system seems straightforward. However, the fact is that the expected length of all fabric springs and stitching springs are unknown. A standard mass spring system typically assumes that the fabric springs have the expected lengths equal to their original lengths. Yet, this assumption does not hold for the extremely coarse system for smocking. When the fabric bends to create pleats, the expected length at the final state depends on the unknown pleat formed in between. Additionally, determining the expected length for the stitching springs is also non-trivial. Most cloth simulators assume the sewing threads are fully tightened and expect the stitching springs to be 0 in length. However, in practice, Italian smocking intentionally loosens the sewing threads for aesthetics and structural support. To address these challenges, we propose to solve the 2D projection of the system dynamics. The projected length of each fabric spring is bounded by the fabric thickness and its original length. This constraint allows fabric springs to compress in 2D to form 3D pleats. For a list of connected stitching springs, their overall length is bounded between the total thickness and a predefined shrinkage ratio gamma of the sum of their original length. This gamma allows us to mimic the smocking process under different shrinkages. We propose an efficient algorithm to solve the 2D dynamics that satisfies these constraints. Here is a 2D simulation example with the shrinkage ratio gamma set to 10%. It gives us faithful predictions of the projected positions for the stitching vertices. However, the simulation generates only 2D positions and does not include the front and back information. We then sample the midpoint on each stitching spring and assign a height that differs from the initial 2D plane to encode the front and back information. More specifically, a backstitch would make the fabric bend outward, which leads to a positive height of its midpoint, while a front stitch has the opposite effect. Next, we use the calculated positions of the stitching nodes and their midpoints to guide CIPC in deforming the fabric at a finer resolution. Here are some examples of Italian smocking patterns. Our simulated results show faithful and accurate pleats that are close to real fabrications. During smocking, we observe that small pattern modifications can lead to significant pleat changes. Our method can accurately preview such smock designs, even with minor changes. This can help artists design and fine-tune patterns in practice. We also offer the flexibility to adjust the shrinkage ratio of the fabric in our configuration. Compared to CIPC under different settings, our method produces more regular and realistic pleats. In conclusion, we formalize the Italian smocking design and propose a practical method to preview the smocked design in this work. It achieves faithful results compared with real fabrications. Thank you for your attention. Please see our paper for more details.